Hello dear learners, welcome back to our channel. I am Dr. Vandana Yadav from Faculty of Science, the Bhopal School of Social Sciences, and today we are going to start with our another topic, which is molecular orbital theory in case of heteronuclear diatomic molecules. In this we are going to study what is heteronuclear diatomic molecule, key features, condition for linear combination of atomic orbitals, types of molecular orbitals, their filling order and MO diagram of NO and CO. So, moving on to our first part, what is heteronuclear diatomic molecules. So, as you can see in the picture that I have drawn AA and AB. So, basically heteronuclear diatomic molecule means when two different atoms are present in a molecule, then it becomes heteronuclear diatomic molecules. Like in this case you can see A and A, they are identical. So, therefore, this is homonuclear, same type of atoms are forming a molecule. However, in this case you can see that one is A, one is B, they are forming a covalent bond. Now, because A and B both are different, so there will be what the two non-identical atoms interact to form the chemical bond and they do not have the same energy. In this case we can say that B is more electronegative than A. Therefore, the bond or the covalent bond in this case becomes what? It becomes slightly polar in nature. So, therefore, in case of heteronuclear diatomic molecules, the covalent bond is polar covalent bond. However, in this case it is a non-polar covalent bond. So, now heteronuclear diatomic molecules, as you have seen, there is a partial charge development due to the difference in the electronegativity. So, what we are going to see that when we are drawing the MO diagram, as we have seen in case of homodiatomic molecules, we basically draw both the atoms at the same level. Why? Because both are same type of atom. So, as you can see that this is the case of homo or same type of atom, but this is not true for the heterodiatomic molecules. Why? Because A is less electronegative and B is more electronegative. So, what we will do, because B is more electronegative, then B is kind of drawn at the lower energy level. So, we will draw A at slightly higher energy level and B at slightly lower energy level, and then we are going to draw their molecular orbital. So, from the diagram, as you can see that the energy of more electronegative and this is less electronegative, and these are bonding molecular orbitals and these are anti-bonding molecular orbitals. So, this is one of the difference while we are drawing the MO diagram for heterodiatomic molecules, that more electronegative atom is drawn slightly at the lower energy level in comparison to the one which is kind of less electronegative. So, now moving on to the important features are that atomic orbitals of element B, you can see, are uniformly lower in energy than the corresponding orbitals of A, as you have seen in the diagram. Now, basically the electron density of bonding electron is likely to be more closer to electronegative, as I have told you that A and B being more electronegative, this bonding electron pair shifts more towards the more electronegative substituent. Hence, in this way molecular orbital theory can easily describe or easily explain the presence of polar covalent bonds. Polar covalent bond. So, we have clearly indicated that with the help of MO diagram. So, now let us move on to the Conditions for linear combination. Conditions for linear combination in this case are same as that in case of homodiatomic molecules. First thing you have to remember is that same energy of combining orbitals, same symmetry about the molecular axis, and proper overlapping between the atomic orbitals. As I told you, proper overlapping means if I am combining S, then forming sigma, if P and P, then this is sigma, but if there is sideways overlapping, then this is going to form a pi bond. So, conditions for linear combination of atomic orbitals remain the same as in the case of homodiatomic molecules. Same number of or same type of molecular orbitals are formed: bonding, antibonding and non-bonding. Now, let us have a look at the order of filling. So, order of filling, as if you remember in case of homodiatomic molecules, if atomic number is 14 and second one is if atomic number is 15 or above. So, first order is what? The order is sigma 1s, anti sigma 1s, sigma 2s, anti sigma 2s, then we have pi 2px, pi 2py, sigma 2pz, and then we have anti pi 2px, anti pi 2py and anti sigma 2pz. This is the order for atomic number 14, and in case of 15 you can see that it changes: sigma, anti sigma 1s, sigma 2s, anti sigma 2s, and now instead of pi we have sigma 2pz at kind of lower energy level, then we have pi 2px, pi 2py, and then anti pi 2px, anti pi 2py, and then anti sigma 2pz. So, order of filling remains the same, but we have two categorization. One is for atomic number 14, another one is for atomic number 15 and above. So, this is the order of filling we have seen. Now, bond order, as we have already calculated this in case of homodiatomic molecule, that number of bonding electrons minus number of anti-bonding electrons divide by 2 will give us the bond order, and basically it will give us an idea about the number of bonds being formed. So, now let us draw the MO diagram for CO molecule. So, MO diagram for CO molecule. Now, looking at the CO, carbon is having 6 electron, oxygen is having 8 electron. So, total we have 14 electrons. Configuration is 1s2, 2s2, 2p2, and in this case we have 1s2, 2s2, 2p4. So, what we can say, 1s and 1s is going to combine, 2s and 2s is going to combine, and 2p and 2p is going to combine. As I have told you, the total number of molecular orbitals formed will be equal to total number of atomic orbitals combining. So, starting with the MO diagram, I am starting with the 1s. So, 1s for carbon atomic orbital and slightly lower energy level of oxygen. As you all know, oxygen is more electronegative than carbon. Then this is your molecular orbital being formed. So, this is sigma 1s and this is anti sigma 1s. Similarly, 2s and 2s for oxygen. This is 2s2, 2s2, this is for carbon, this is for oxygen, then we have sigma 2s and we have anti sigma 2s. So, filling up the electrons 1, 2, 3, 4, 5, 6, 7, 8. Now, moving on to 2p1. So, we have 2p2 this side. So, we have 1 and 2 and we have 2p4 this side. So, 1, 2, 3 and 4. Now, because it is 14 and as we have seen in the filling order, then lower energy will be occupied by pi, comparatively higher energy by sigma, and we have anti pi and anti sigma. So, this is anti pi 2px, this is anti pi 2py, and this is anti sigma 2pz. Here we have pi 2px, pi 2py and sigma 2pz. So, this is 2p2 for carbon, this is 2p4 for oxygen. Now, try to fill the electrons to this side and 4 this side, to total 6. So, starting 1, 2, 3, 4, 5 and 6. So, completely filled bonding molecular orbital. So, now if I going to write your MO configuration, so MO configuration will show me sigma 1 S2, anti sigma 1 S2, sigma 2 S2, anti sigma 2 S2, and now pi 2px is also filled, pi 2py is also filled, and you can see sigma 2pz is also filled. Calculating bond order, count the number of bonding 2, 4, 5, 6, 7, 8, 9, 10. So, 10 and antibonding 2 and 2 4, minus 4 divided by 2. This will be your bond order, and you can see that all are paired, all the electrons present in the molecular orbitals are paired. So, this is kind of diamagnetic in nature. So, this is diamagnetic in nature. So, now moving on to, you can see it is 3. So, moving on to next molecule, I think CO is clear. Moving on to the second example of MO, heteronuclear diatomic molecules, that is NO molecule. So, NO molecule, we will start with NO molecule. So, we have N plus O, N is having 7, oxygen is having 8. So, total number is 15. So, in this case now we are going to follow the second order of filling. So, for 7 we have 1s2, 2s2, 2p3 and 1s2, 2s2, 2p4. So, 1s and 1s, 2s and 2s, 2s, 2p and 2p. So, starting with 1s, this is for nitrogen, and in this case also you know that oxygen is more electronegative than nitrogen. So, atomic orbital of nitrogen and this is atomic orbital of oxygen, kind as slightly lower energy level. Draw this, this is 1s2, this is 1s2, this is sigma 1s, this is anti sigma 1s. So, 1, 2, 3 and 4. Now, moving on to the 2s and 2s, 1, 2, 1, 2, 2s2, 2s2 and we have 1, 2 sigma 2s and 1, 2 anti sigma 2s. Now, moving on to 2p, as you can see in here the 2p is what? 2p is having 3 and that side it is having 2p4. So, 2p3, 1, 2, 3, 2p3 and this is 1, 2, 3 and 4. So, now because it is having 15, so this time the order of filling is slightly different. At the lower energy level we are going to have sigma 2pz and then we are going to have what? We are going to have pi 2px and pi 2py, and at higher energy level we are going to have anti pi 2px, anti pi 2py and we have anti sigma 2pz. Now, start filling the electrons, 3 this side and 4 this side. So, 1, 2, 3, 4, 5, 6 and 1 will either go to pi 2px or pi 2py. So, now if I write the MO configuration of this molecule, it is sigma 1s2, anti sigma 1s2, sigma 2s2, anti sigma 2s2. Now, look at this, sigma 2pz2, pi 2p 2x2 pi 2py2, and now in this case we have one electron present in either 2px or either 2py. So from the MO diagram you are clear that because there is one unpaired electron present in anti-pi orbital, this structure or this molecule is paramagnetic in nature. You can also calculate bond order, which is number of bonding. To count the number of bonding, 2, 4, 5, 6, 7, 8, 9, 10. So 10, and anti-bonding involves 2, 4 and 5. Minus 5 divided by 2, this becomes 2.5 divided by 2. So this is your bond order for NO molecules. I hope you are clear with the diagram of NO and CO molecule. The only difference is that the more electronegative one is drawn at a slightly lower energy level in comparison to the less electronegative atom. Now the question arises, we have many molecules which are existing. So now can you draw the molecular orbital diagram for HF molecule? Can you draw the, because HF molecule do exist, and if I draw the H and F, so H you know it is having 1 electron and F is having 9 electron. Configuration, if we draw it is 1s1, and for this which is 1s2, 2s2 and 2p5. So now think about it, how we can draw the MO diagram for HF molecule, because here we are having only 1s1 and here we are having 1s2, 2s2, 2p5. There is formation of covalent bond, as you all know HF do exist. There is formation of covalent bond by sharing of electron. This is what? This is polar covalent bond. But how we are going to draw the MO diagram of HF molecule? Think about it and we will discuss this in our next lecture. Till then, happy learning, stay safe.